Okay, good afternoon, good morning, good evening from wherever you are in the world. I guess since we're virtual, I can't make any assumptions about the time zone. There are still attendees trickling in, but I think we're going to go ahead and get started. So the talk today is titled Lowering the Barriers to Industrial Control Systems Security with an open source software package that was created by uh, my group at Georgia Tech, as well as my company, Fortiphyd Logic. So next slide. Okay, so this is a title slide that has some of my affiliation information. So I wear a number of different hats, and I'll just sort of enumerate those now. My name's Raheem Beyah, and I am a professor of electrical and computer engineering at Georgia Tech. I'm also the executive director for our online master's in cybersecurity program at Georgia Tech, and I'm also the vice president for interdisciplinary research for the institute, so for Georgia Tech. And in addition to that, I have a company that does industrial cybersecurity called Fortiphyd Logic. As I mentioned earlier, my research group, as well as folks at the company, work together to develop and release an open source system called GRFICS, which I'm hoping to get you excited about today. Next slide. So I always like to give a very brief commercial when I have an audience. So in my research lab at Georgia Tech called the CAP Lab, the Communications Assurance and Performance Research Lab, we focus primarily on cyber physical system security. And within that space, there are really two main buckets of work. So one is industrial control system security, and that's the topic of discussion today, even though this is an education related topic. And the other is additive manufacturing, so attacking and securing the 3D printing process. We also do a lot of work in network performance and characterization, in privacy, in terms of structured data privacy, preserving and also destroying systems. So we also attack these systems. And then cybercrime, we've done some work in that space. So our approach is actually quite similar to most folks in the research, cybersecurity research field. So we design real world systems and tools and algorithms that are immediately applicable, right? So we have lots of cybersecurity problems today. We all know that. But as an academic, I also have to focus on what's next. What's the next network and next device? And then what are going to be the attacks on the sort of next generation system? So we take this sort of two-pronged approach. Next slide. All right, so GRFICS, the graphical realism framework for industrial control systems. So you see like a snapshot of the graphic system in front of you. And I'm going to give you more details about what this actually is in the coming slides, and also how it can be used specifically in the education environment. Next slide. Right, so why did we do this? I teach a cyber physical system security class in our online master's program, and also on campus when I get an opportunity to teach on campus. And I wanted to be able to demonstrate to students the consequences of a true attack on an industrial control system. And as I started digging and trying to figure out how to do that, I realized that it was really hard to find systems that were realistic. So I looked at a bunch of different systems. There were lots of things that were specific to IT. So you have the Kali Linux VM, for example, with offensive security tools and other defensive tools that are there. But actually very little that was specific for industrial control systems, right? So the training that's out there, the platforms out there are the training is pretty much very expensive. You have like a SANS training, which is 7K or so. You got to fly out there for this training. And then, it's hard to, let's say, even when you do that, you're doing and go to different places for trainings, you have, this small PLC, and some LEDs that start blinking when something bad happens. And that, that really doesn't really drive home the consequences of various attacks. So we wanted to develop something that, again, motivated from me in my class, that I can help my students understand, hey, here are consequences, real physical consequences of an attack on an industrial control system. And it's not just lights blinking. So that's kind of how it all got started. And we wanted to make sure that we open it up to the public. So we've written a technical paper on it that was published at USNIC's security, the education workshop associated with it. And then we also have the source code that we are actually doing a pretty decent job maintaining on a GitHub site, which I'll point you to at the end of the talk. Next slide. So here are the key contributions. We converted a simplified Tennessee Eastman challenge process to, from Fortran basically to C++, right, to make it much more portable and accessible. And I'll talk a lot about what this is shortly. You actually visualize a 3D environment of a dynamic chemical process. So the process that we chose was a chemical process. We actually run a real process that had process physics that's there, and that's the Tennessee Eastman process. And it's actually fairly real. And so when you can actually attack the process and destabilize the process and ultimately cause an explosion if, let's say, the pressure in the reactor increases too much. It's one of the most complex and complete virtualizations of an ICS network to date. And it's free, open source, right? Can't beat that. And it has a modular framework, right? So you can easily expand things. Now, I'll highlight that when I get to the general area and the architecture of the system, where you can just pull out protocols, plug in new protocols, pull out a process, plug in a new process. Next slide. So there's been some related work. I talked a little bit about it earlier, and most of it had been in like various test beds, right? So actually, I have colleagues that I work with at the Singapore University of Technology, and they've actually developed a really nice water distribution test bed and also a small scale electric power grid network. So again, that's actually fairly realistic, but I can't destroy the test bed, right? I mean, that's not, I don't think I would be they would not invite me to use their systems again, right? So we want to show real significant consequences. So you can go and do some experiments, but none that are of significance, right? None that are potentially catastrophic. And then also the DOE has developed this national SCADA test bed. There are some sort of digital techniques that are out there. So for example, there was a open PLC project that's been going on for the last 7 or 8 years or so, and I think it's on version 3 now. But that's a programmable logic controller, and it is virtualized. But the problem is that it was most of the works that used it didn't connect it to a larger, more interesting environment. So like to a 3D environment that represented a real process. And so that's what we want to do, was to take all these pieces, bring in real network protocols, realistic looking environments, all the various components of an industrial control system in a way so that you can go and launch various attacks, practice defending against attacks, and so you can teach students how to leverage in various types of attacking systems. Next slide. All right, so here's an overview of ICS Networks for those that don't have the background in ICS. So you have what's called a human machine interface, the HMI. And this is usually sort of a 2D screen that's almost a picture of the environment that you're simulating, right? So if it's a chemical reactor, it's a 2D version of this chemical reactor, and you can actually click on them, click on different points and modify the process. When you want to modify the process, that goes to the controller or the PLC, which has a logic. That logic will determine when you make changes to the process, like doing things like modifying actuators, like valves, for example. If I want to, do I want to open or close certain valves? Well, this controller will control that. That affects the physical process. Let's say if the pressure gets to be too high in the reactor, I might want to open the valve associated with that. and release and pressure, or same thing with temperature, et cetera. And of course, I have my sensors that measure the physical process and give me feedback about the physical process. And then that goes back into the controller, and the controller will again make decisions based on this sort of closed loop analysis that occurs, right? So you can think of, any physical process from water treatment to manufacturing to power grid. This is sort of a general description of a physical process. Next slide. Okay, so graphics is modular. I've mentioned that already. It has essentially all of the main components of industrial control systems. So an HMI, human machine interface, a PLC, various IO modules, which are used to communicate from the process to the rest of the system. And also real network, ICS network protocols that you can actually use Wireshark and monitor the traffic between the various ICS components. The physical process simulation is tied to the 3D visualization and IO module layer using JSON, just a really intuitive way to exchange information from the process in the 3D visualization. Next slide. So here is the just the high level architecture of graphics, and it uses 3 different VMs. So this is this top box represents the VM that's used for the HMI, and it's an open source human machine interface. And also, if you wanted to do the PLC editor, you modify the PLC code there as well. Then you have another virtual machine that runs the PLC, the open PLC. And then you have another virtual machine which runs the process, and these are running Ubuntu. If you look at the virtual machine that runs the process, you'll see that it's fairly layered and structured, making it just modular by design. So we have this simplified Tennessee Eastman simulation that we worked on. We converted from a much more complex simulation. But let's say I want to replace that with a power system simulation, let's say a distribution substation or power generation substation. I simply would need to remove this process, put in the power distribution simulation, populate the correct IO values and connect it to the OpenPLC, and also modify, obviously, the visualization. But once you do that, the architecture, it works just fine, and you now have a new process within this architecture. So the goal was to make sure it's modular. Also, you can remove the PLC, and you can put in various proprietary PLCs, and also PLCs that are hardware PLCs if you wanted to. So the nice thing about this, that is connected using real network protocols, so you can actually rip out this open source HMI if you want it and put in a real hardware-based HMI. So once you have this nice modular architecture, it's like, okay, well, what are the cool things that I can do as an attacker and attack this system, and where can I attack the system? And that's what this represents. So you can do things like brute force weak passwords on HMI, right? It's just a human machine interface. It's where the operator interfaces with machine. You can do things like inject false data, right? So you can, Modbus is a protocol that does not use authentication. That's how one of the oldest and one of the most popular industrial protocols. So you can easily, it has no security associated with it. You can easily just inject packets if you want. You can launch buffer overflow attacks and also do false data injection between the PLC and the process, right? So lots of interesting ways in which you can attack the system. Next slide. Okay, so here is sort of an example network, right? So you have, it starts out as a flat unsegmented network, which is good because when you get to the exercises, you'll see that the goal was to keep it that way so you can have a defense exercise where you actually will build a segmented network. Like it's one of the first things that you would want to do. So it's a flat unsegmented network, meaning everything is in the same broadcast domain. The PLC will interact with the IO modules in the HMI, and then the user supervises the system using the HMI, right? So this is at a high level, how the network actually looks. Next slide. So here's a little bit more meat about the process simulation. And again, we don't want to get too bogged down here because this is just a process. You can pull it out and put in any process, ones that are more complex or ones that are much more simple. But the Tennessee Eastman process challenge was introduced in the early 90s, right? It was a process controlled benchmark simulation, and it can be used, and it was used as a teaching aid to impart practical understanding of process design, dynamics, and et cetera, right? So it was a challenge that's been around for a while, and it was created by the Eastman chemical process. The original process was very complicated, at least more than for us, because we don't want to implement something that was extremely complicated, not for the sort of the proof of concept open source system. It had a total of 12 control valves to manipulate and 41 output measurements to monitor, right? So it was actually fairly complex for us to implement. So what we did was we used the simplified version. Somebody took the original one and simplified it. That was also at Fortran, but then we ported it to C++. And this is the example of the P&ID diagram, which sort of describes the actual process. Here are the various valves that are controlled. There are 4 control valves. They're here, 1, 2, 3, 4. Oh, actually, I don't, you probably can't, I'm not sharing my screen. There are 4 valves that are there in the screen. And then the rest are various components to measure various parts of the process, temperature, temperature, pressure, and other things, and also set points, et cetera. Again, it's not that big a deal to be bogged down with the simulation details. But the point is that it actually is a real simulation that has real process physics associated with it, meaning that, again, if the temperature gets too high, then there are going to be significant consequences. So the pressure gets too high, there'll be significant consequences. And our goal was to be able to demonstrate those consequences in a realistic way. And we hope to show you that. And ultimately, what we want to be able to do is link the network traffic, network attacks to physical consequences, right? So can I link the fact that somebody has injected false data and that this protocol does not use authentication, link that to an actual explosion, right? So we wanted to make that connection. Next slide. So here's a picture of the PLC. So it's Open PLC server. I think it's up to version 3 now, I believe, that we have in the open source version. And this is just the editor for the PLC programming piece. So it takes standard ladder logic. Now that's actually later compiled, but standard ladder logic or structured text, some of the standard languages for a program controller, and then it's ultimately pushed to the PLC where the logic is actually run and executed. This PLC, again, is connected to the process and also to sensors that are monitoring the process. Next slide. Here's an example of an HMI, so the human machine interface. So again, this is a chemical process. So it's just like an image of a chemical process, and you'll see that all the different values that are there are values that are being monitored and measured regarding the process, and also values that you can actually enter. So if you look at the little box down at the bottom right, you can actually enter and send certain values for set points, for example. So this is how standard HMIs look. It just kind of mirrors the process so the operator can go up and visually see what's going on in the process and also make changes and do things like start and stop the process. Next slide. So here's a 3D visualization of the normal operation. If you look to the left, and I know it's probably hard to see, you'll see all the process values that are being measured that are there. So just know that that's a running list that's dynamically changing based on the actual process of things that are being monitored inside the process. And this is a view as if you were standing inside of a warehouse and looking at this chemical reactor, this chemical process occurring, right? So you have these 2 chemicals that you're combining in this process. Some of it you're gonna purge, you're gonna waste, and then you're gonna have this final product that's produced. And your goal is to do this in an optimal way, such that you don't destabilize the process, that you produce as much product as you can, and also that you reduce the amount of waste. So you want to minimize the purge that occurs. Okay, good. All right, next slide, please. So I mentioned that these were real networks, right? So running real network protocols, right? So you actually have um, real Modbus libraries that are being used to communicate. So just to illustrate that, we included Wireshark inside of the open source package, where you can monitor the traffic that's going back and forth, and you'll see that these packets, if you look at it, they are real network traffic. You can create PCAP files from these, and you can easily see by looking at the Modbus traffic, which is I appreciate is hard to view here, that there's no encryption associated with it. There's no authentication. And what that tells me, number one, I can monitor this from the network. If I'm an attacker, if I get on the network, I can sniff the values, let's say even of the process. But even more significant, I can do things like inject commands. So Modbus is used to read information about the process, read the temperature, read other information about the process, but also to do things like control set points and control various values. So I can actually inject packets in the network and cause destruction if I want to. And that's what's really nice about this. And it's a VM, right? So you can just close it and restart, right? You don't burn down the building. Next slide. So, I talked about the consequences. Once you destabilize the process, once you compromise the physics of the process. So here's an example of this sort of realistic feedback that you get from a student. And if you can go ahead and play the video. In this example, the you'll see the red bar next to the reactor has increased to the point, and I believe that's the temperature in this scenario. So it's gotten past capacity, and it's true process physics. And then there's this explosion that occurred, right? So of course, my students love doing this, right? It's like, oh, can I cause explosion? Can I do something else that's catastrophic? But that is sort of genuine feedback to a student. I mean, once they see that, hey, wait a minute, this me typing a command with this false data injection, this software that I'm using can actually cause a physical explosion. Then they actually, put two and two together and say, wow, I now appreciate sort of this intersection of the digital and physical worlds. So this is what we wanted to do, was to make sure that we tied all this together, that they know that here's this physical world, and underneath are all these networking components, these computing components, the protocols, all of this stuff, and they're deeply interconnected. Next slide. So, I've talked in general about this sort of high level environment that we created. And what's nice about it, I mean, remember, it has, real network protocols. It's running real operating systems. And so it's really its own contained sandbox, if you will. And so you can overlay various exercises on top of it, because most of the tools that work in the real world will work in this virtual environment, right? So here's some example exercises that you can do, right? So basic simple stuff like password cracking, right? Using your favorite password cracker. Reconnaissance, right? So launching man-in-the-middle attacks. So maybe you want to sit in between the HMI and in the PLC, right? That allows you to monitor traffic and also inject, maybe using EtherCap, inject malicious commands. The Modbus command injection, I mentioned that. You can modify the code on the PLC, right? So if you think about like Stuxnet, for example, one of the most significant and first sort of major ICS attack, and then Triton, which is a more recent, about 2 years ago attack. So those attacks came in and modified the logic on the PLC, so you can actually do things like compromise an engineering workstation in Windows, pivot, connect to the PLC, push new code, new logic there, and actually compromise the logic on the PLC and have that destabilize the process, right? Or you can do things like buffer overflow attacks. Again, these are running real operating systems. From a defensive perspective, things that you can do, network segmentation is really basic stuff, right? I mentioned this was a very flat network, so network segmentation. We also have the standard IDS tools installed, like Snort, for example, so it allows you to, monitor for different types of attacks, and you can do both of these in parallel, right? So the offensive and defensive piece, and then whatever else you can think of, again, you can probably do here, because these are real network protocols and real operating systems that are in the environment. Next slide. So, so that's kind of the summary of the open source version there, which has its own open source quirks. We support it to a certain extent. There also is a commercial version that we use. That you can do things that competes with, like a SANS training, right? So the cool thing about the commercial version is that it has other processes, right? So this is a natural gas generation process. It has a water treatment plant. It has manufacturing. It has a data center, and I think there are several other processes that are there. And it's the same sorts of attacks that you can do. This one is much more, the commercial version is much more formal. It has a learning management system and everything connected to it. So it's really involved, sort of nice extension, and it's a fraction of cost of like a SANS, and the education version is a fraction of that. So it's a really nice product. Next slide. So, in conclusion, I think we all appreciate that there is a shortage of cybersecurity professionals, and even when you go into even further shortage, when you go into specifics in these industrial systems, there just are not enough people that understand the physical process world and the cyber world, and understand the intersection of the two. So there's just a significant shortage of folks there, and I think we all appreciate that. So we developed this framework, hopefully to reduce that, right? So it's an open source, free and open source version that's out there that you can download right now, and there's also, again, a commercial version if you want to not deal with all the quirks with open source software. We use Unity 3D to visualize the system, so it's in a realistic way, and also demonstrated some example exercise. How can I attack the system? How can I defend? But I hope you appreciate that you can pretty much put any exercise on top of, or overlay that on top of this environment. Future work that we're hoping to push some of the things that we have in the commercial version to a certain extent to the open source version. So the water treatment is already there, manufacturing is in the commercial version, and we're hoping to have a scaled down version of that to push to the open source. Right now, open source only supports a chemical, but we're hoping to continue to support it, and also add things like other components, like historians. Historian is already, which is just a database that stores historical values. That's already in the commercial version, and we're hoping to push that to the open source version. Next slide. So that's it. You can see my URLs here, and email addresses, and Twitter. And the most important thing is the GitHub. So if you want to go and play with this, you're welcome to do so. And I would love to get your feedback and your thoughts. We're working to improve it as much as we can. So thank you, and I will stick around. I think we have some time. I'll stick around. I'd love to get your questions and comments. All right, I see one question, and it looks like I hope, Thomas, I answered your question. There is a distribution, actually it's a transmission substation scenario that's in the commercial version, and at some point we expect it'll make it over to the open source, but it'll probably be a while, but it's available now in the commercial version. What else? Any other questions? I'll stick around. Let me see. Okay, here we go. J at INL. Oh, great. Yeah, I know lots of folks out there. Yes, Jay, the open source version is available right now. You should be able to go to that GitHub link. Jay to ask, is the open source version available? Absolutely. You should be able to go to that link. If it's somehow broken, let me know. But I think it's up there, and you can feel free to play around with it, modify it, and do all the fun stuff you want with it. You guys do lots of great stuff out at INL. Okay. Let me make sure. All right, I think we're good. All right, so I think I'll let you all get back to browsing. I hope you enjoyed the session. And again, you have my email addresses. If you want to talk about the open source, please just email Gotek. If you want to talk about the commercial one, email the Fortiphyd, and I'll get you to the folks there, and you get a chance to play around with both. They have demos that they give at the company with the LMS and all that other good stuff. So feel free to shoot me an email, and hope you enjoyed the talk. Thanks, everyone.